talking about the binding energy of particular nuclei, and we've worked out the binding energy of carbon-12, and we worked out that it was 92.16 mega electron volts. Okay, so that's the binding energy, if we call it Be, of carbon-12. Now we've also know the binding energy of helium-4, because earlier on we worked out that the mass defect of helium was 0.03037. So if we multiply that by 931.5, then we can work out what its binding energy is. Okay, so if you do that, you're going to do 0.03037 multiplied by 931.5. That gives you 28.29. So 28.29 mega electron volts. So we know that the binding energy of helium 4 is 28.29 mega electron volts. So this has a bigger binding energy, carbon-12, than the helium. Okay, so fair enough. Now, so that's the total energy required to pull all of the nucleons out, all 12 of the nucleons out of the nucleus and separate them. That's the total energy required to pull all 4 of these nucleons out and separate them. This is obviously bigger because there are more nucleons to pull out, and each of those requires some energy. Okay, now the binding energy is a useful term, but more useful is the binding energy per nucleon. That's the average energy required to pull out each individual nucleon. So if I was to work out the binding energy per nucleon of carbon-12, it would be the average energy required to pull out one of the nucleons. If I work out the binding energy per nucleon of helium, it's the average energy required to pull out one nucleon, whereas this is the energy to pull out all 4, and this is the energy to pull out all 12. Okay, now the binding energy per nucleon is the average energy needed to remove each nucleon from the nucleus, and it's a useful concept because it allows us to compare how stable these nuclei are. Okay, so let's actually do that. Let's work out the binding energy per nucleon for carbon-12 and for helium-4 too. Okay, so for helium-4 the binding energy is 28.29. So the binding energy per nucleon is going to be equal to 28.29 divided by 4. Okay, so 28.29 divided by 4, and that's going to give us 7.07 mega electron volts. Okay, now for carbon-12, the binding energy per nucleon is just equal to its binding energy, which is 92.16, and then I'm going to divide that by the number of nucleons, which is 12. Okay, so it's the binding energy divided by the number of nucleons. So 92.16 divided by 12, that's going to give me 7.68 MeV. Okay, so you can see that carbon-12 has a larger binding energy per nucleon than helium-4. And what that means is that carbon-12 is more stable. If I want to pull out one nucleon from carbon-12, it's going to require 7.68 mega electron volts on average, whereas to pull one nucleon out of helium-4 requires 7.07 mega electron volts on average. So it requires more energy to pull out one nucleon from carbon-12 on average than it does to pull out one nucleon from helium-4 on average. That means that this is more stable. Okay, the nucleons are more tightly bound together. They're in a lower energy state. Okay, they've got less potential energy than the nucleons in helium-4. Now you can see here with these two examples, as the nucleus gets bigger, the binding energy per nucleon gets bigger. But that doesn't happen for every element. Okay, once you get to a certain point, you reach a maximum. So let's have a look at that now. Okay, so we've been talking about binding energy per nucleon, and we've calculated the binding energy per nucleon of helium-4 and we also calculated the binding energy per nucleon of carbon-12, and we found that carbon-12 had slightly more binding energy per nucleon. This graph is the average binding energy per nucleon on the y-axis against the number of nucleons, or the mass number, or nucleon. Oops. On the x-axis. So on the x-axis we've got the mass number or the nucleon number, and on the y-axis we've got the average binding energy per nucleon. And what you find is this. Hydrogen has a number of isotopes down here with a low binding energy per nucleon, but as you go up, as the mass number increases, the binding energy per nucleon increases rapidly up to helium 4-2. Then you get a little drop down to lithium, and then back up again to carbon, and then back down a little bit, back up to oxygen and back down. So there's these little peaks here which are anomalies, so to speak. But generally speaking, the binding energy per nucleon increases rapidly up to a peak here as the number of nucleons in the nucleus increase. So you don't need to know why these spikes are here, why you've got these anomalies for helium, carbon and oxygen. If you want to look it up, it's all to do with the fact that the nucleons in the nucleus sit within certain shells, which are all to do with quantum number and so on. And when those shells are full, which is the case with helium, carbon and oxygen, you get an increase in the stability and therefore an increase in the binding energy per nucleon. But you don't need to know about that. All you need to know is that as the mass number goes up, the binding energy per nucleon goes up to a peak. And iron 56 sits at that peak. Iron 56 is said to be the most stable nucleus, and it's got a binding energy per nucleon of 8.7906 mega electron volts. Now, complicating matters slightly is the fact that actually nickel 62 has a higher binding energy than iron 56 at 8.7948 mega electron volts. But usually we say iron 56 has the highest binding energy per nucleon. Okay. Now, once you get beyond iron 56 at the highest binding energy per nucleon, the binding energy then decreases with mass. Not rapidly, but it decreases gradually with mass up to your highest mass nuclei like uranium. Okay, so low mass nuclei, rapid increase in the binding energy per nucleon up to iron 56, and then a gradual decrease down to uranium-235, a decrease in the binding energy per nucleon. Okay, so what this means is, remember, the greater the binding energy per nucleon, the greater the amount of energy required to remove one nucleon from the nucleus. So iron 56 requires the most energy of all elements on this graph, discounting nickel. So iron 56 requires the most energy of all elements to remove just one nucleon from its nucleus. Okay, so you can see here that helium has a binding energy per nucleon of about 7 mega electron volts, whereas iron has about 8.8 mega electron volts. That means to remove one nucleon from helium would require 7 mega electron volts or thereabouts, whereas to remove one nucleon from iron would require 8.8 mega electron volts. That means that the nucleons are more tightly bound in iron. It's more stable. Okay, the bigger the binding energy per nucleon, the more tightly bound the nucleons, the more energy required to remove one nucleon, the more stable the nucleus. Okay. Now, the next thing to say is this. The binding energies, you'll notice, for most nuclei are between about 5 and 9 mega electron volts. So if you know that, that's useful, because when you do any calculations then of binding energy per nucleon, if you find that you get some number that is not between 5 and 9, then you know you've probably gone wrong. Unless it's for one of the isotopes of hydrogen or helium-3, because they have lower binding energies per nucleon than 5 mega electron volts. Okay, so that's what this graph shows us. This is the most stable nucleus. Okay, and ideally, obviously, the more stable the nucleus is, the better. Okay. Now, what we need to do now is try and understand why it is that beyond, obviously, as we get more nucleons in the nucleus up to iron, there's a greater binding energy per nucleon. Why is it that beyond iron, the binding energy per nucleon decreases? Why is that the case? Okay, well, it's pretty clear why the binding energy per nucleon increases as we get more nucleons. That's because the more nucleons there are, the greater basically the greater the effect of the strong force, because there's more nucleons and there's a greater strong force overall, and therefore the more tightly bound these nucleons are. The question is, why does the binding energy per nucleon decrease beyond iron? And the reason for that, so the strong force, okay, just to recap, is about 50 times the size of the electromagnetic force in strength. The strong force is attractive over distances up to about 1 femtometer. Okay, that's 1 times 10 to the minus 15 meters. The electromagnetic force is repulsive over very large distances. So although the strong force is greater than the electromagnetic force at small distances like this, the electromagnetic force can occur over large distances. Right, so what's going on here? Well, if you take a small nucleus like this, I know it looks like helium, but let's just forget about what they are. These are just small nucleus, large nucleus, okay? If you think about it, each of these 4 nucleons is attracting each other. So this one is attracted to this one, this one's attracted to this one, this one's attracted to this one. They're all attracted to each other with a strong force, okay? Because they're all separated by a really small distance. But these two feel the electromagnetic force, and they're being repelled from one another, okay? So they're all being attracted by each other with a strong force, but these two are being repelled. Because each of the 4 attract each other, every one of these nucleons, feels the strong force from every other of the nucleons. The strong force dominates. The strong force is greater than the electromagnetic force, okay? Now, here's the issue. As the nuclei get bigger, the distance between nucleons at either, at the extreme ends of the nucleus is greater. So that means that these 2 nucleons here experience a very small attractive strong force. But these 2 nucleons here experience a fairly large electrostatic repulsion. So these 2 are attracted by a fairly small force. These 2 are repelling each other with quite a large force. So that means that for larger nuclei, the electromagnetic force increases, the electromagnetic force of repulsion increases more than the strong force of attraction increases. So the more nucleons you put in a nucleus, the strong force will increase, there will be a greater strong force overall because there are more nucleons attracting each other. But as the nucleus gets bigger, although the strong force overall increases, the electromagnetic force of repulsion increases more because it can act over larger distances. So these 2 only experience a very small strong force of attraction, whereas these 4 will each attract each other with a strong force quite strongly. But the problem is these 2 nucleons here, these 2 protons here, are repelling each other with quite a large force. So the electromagnetic force, as a nucleus gets bigger, increases more than the strong force increases, and that means that the strong force is still bigger than the electromagnetic force, okay, but by less. So you could say here that the strong force is much bigger than the electromagnetic force, if we just want to make it simple, but the strong force here is only a little bit bigger than the electromagnetic force, okay? Now, as nuclei get bigger, to overcome this issue, what you find happens is they tend to have more neutrons in them, okay? So the bigger, this is obviously, we're talking about elements here bigger than iron. I've just drawn a small, I obviously haven't drawn this as a with the correct number of nucleons in it, but I'm just drawing it as an example, okay? So think of this as a really big nucleus, bigger than iron. What tends to happen in those really big nuclei is that they have more neutrons than protons. And the reason they have more neutrons than protons is because that increases then the strong force, because each of these neutrons attract each other with a strong force, but they don't experience electromagnetic repulsion. So by increasing the number of neutrons, you increase the strong force without increasing the electromagnetic force. So what we're saying is really large nuclei need more neutrons in order to keep them stable. Okay, they need more neutrons than protons in order to keep them stable, because the more neutrons you put in, the greater the overall effect of the strong force, but it doesn't increase the electromagnetic force, because as we know, the electromagnetic force is acting over really big distances. Okay, so I hope that makes sense. It's a bit difficult to explain that, but I hope that makes sense. Okay, so that is why that up to here we get an increase in the binding energy per nucleon, because the more nucleons there are, the greater the strong force, and that dominates over the electromagnetic force. But once you go beyond iron, the electromagnetic force increases more than the strong force does, so therefore the nuclei, although they're still stable, they're not as stable as iron. Okay, iron, you could say, has got sort of the perfect or the ideal mix of protons and neutrons, and it has the biggest difference between the strong force and the electromagnetic force. Okay, it's got the biggest difference between the strong force and the electromagnetic force. Okay, I hope that makes sense.